Test, test, test. All right. Okay, so I'm just going to speed through this, and then we're just going to do the problems because I really don't have too much time. Okay, so, all right, we'll go through the definition of a vector space. So a vector space is a module. No, anyways. Okay, so you have this closed so you have two operations. You have a set, you have two operations, addition and multiplication by scalars. Okay? And those scalars are usually in some field. Now you have and for this whole chapter is just real numbers. So you can just think of them as real numbers. Now we have a closed operation which is plus, and the plus is commutative and it's associative. Also we have additive identities. Okay, we also have an additive inverse. All right, so that's chill. Then we have scalar multiplication is closed. Then we have distributivity of scalars over vectors. And now we have distributivity of vectors over scalars. Then we have associativity of scalar multiplication. And finally, we have multiplicative identity of scalars. Okay, so that's great. Then you can easily prove these things like the scalar 0 times u is equal to 0. Scaling the vector 0 by anything is still 0. And then we just define this minus sign equal to -1 as a scalar times the vector itself. Then we get into a bunch of pretty cool examples. So the first example is just Rn, which is nice because it's like, okay, this is the most familiar of the examples because we've been working on it for the past month or whatever. The second example is you remove the coordinate system and you just think about arrows with direction, and then you draw pictures as the geometric proof. And so so that one's pretty cool. This one's nice because it introduces you to something a little more abstract, which is the set of signals is how they call it. And it's basically infinite sequences. And you can show that an infinite list is a vector space. Then the other one is polynomials of some, at most some degree, and you can show that that's a vector space. Then here's another good example, basically all real valued functions, and that ends up being a vector space as well, and you easily show that you can, add two functions that are real valued, and just by adding basically their expressions together. And similarly, you can do scalar multiplication of real valued functions. So, okay, then we get into subspaces. And now we already did subspaces, but now they're just generalizing subspace from Rn to an abstract vector space V. And so it's the same as before. For some set to be a vector space, or I mean a subspace of a vector space, it needs to have 0. It needs to have its elements closed under vector addition. So, for any u and v in H, the sum of u and v is also in H. And then finally, H is closed under scalar multiplication too. So any vectors that you have in H, you should be able to scale them arbitrarily and stay in H. And so then they say a bunch of words here. The set consisting of only the 0 vector. Okay, this is a good example. It is a vector space because you can add 0 plus 0 and you stay in your set. You can also scale 0 by anything and you're still 0. So therefore, the set 0 is and it can be a vector. It doesn't have to just be a single number, but whatever 0 represents in your vector space, 0 is always a subspace. Okay, then they show that the polynomials of bounded degree are a subspace in the set of all polynomials, which is cool. Then this one was kind of interesting. I don't know why they're talking about this one, but this one's cool. Is the set of finitely supported signals. So basically, you have these infinite length signals that go on infinitely to your left and to your right, but only finite only a finite number of the values are non-zero, and apparently that ends up being a subspace of and that one's actually, let's read this one. The set of finitely supported signals S sub f consists of the signals yk where only finitely many of the yk are non-zero. Since the zero signal is zero, has no non-zero entries, it is clearly an element. Okay, that's true. So, that's the first step of proving something's a subspace. Then if two signals with finitely many non-zeros are added, then the resulting must have finitely many non-zeros. Similarly, if a signal with finitely many non-zeros is scaled, it will still have finitely. So, okay, so I mean, that's all you had to do to show that it's a subspace. And it's pretty cool because showing something as a subspace is a lot easier than showing something as a vector space, because you only really have to show these three things as opposed to making sure that all of these 10 things are proved. Okay. Okay. Then they go back. Oh, here's an important example, I guess. R2 is not a subspace of R3, but this, where you have 3 coordinates but only the first 2 vary, that is a subspace. It's because you just can't compare R2 and R3. It just doesn't really make sense. Okay, then they go and they sort of redefine subspace and span. It's sort of like going back through all we learned about span and Rn and just changing the word Rn to vector space. Oh. And okay, so so span is just defined as any linear combination of your spanning set, and you can take 0 because you just take their coefficients to be 0. You can show that it's closed because it's defined as the linear combination closure, so you can scale them and add them together. All right, so then they just, here's the theorem. If some V1 to VP are in a vector space V, then the span of them is a subspace. So any set of vectors in a vector space their span forms a subspace. And we call span V1 to VP the subspace spanned or generated by V1 to VP. Given any subspace H of V, a spanning or generating set is a set that equals that set. That span equals that set. Okay, here's a good example because it's a little computational. So we have this formula for a 4 vector, a minus 3b, b minus a, b. And we do this thing that we used to do, is just a parametric vector form or whatever it's called, where you write it in terms of column vectors. And you can see that since you only need 2 column vectors, this must be, well, first off, it's a subspace because it's represented as a linear combination, but it's also, oh, yeah. So that's all you have to do. Is you have to show that H is a subspace of R4, and we did that by writing them as linear combination of 2 vectors in R4. And since this is the definition of span, and by theorem 1, is that theorem 1? Then this is V1, this is V2, therefore this is a subspace. Okay, now we can finally get to the problems. So I want to do this on the whiteboard because I'm having... Unfortunately, I got to work out a way to get this mic over to me, but keep the camera on the table, but whatever. All right, so let's just answer these. Well, let's go through them, and then I'll write down which ones I want to do on the board. Because I'm guessing, and this happens for most of them, most of the problems just really don't need to be done on the board. Yeah, let me get a pen. All right. Show that the set H of all points in R2 is not a vector space. Okay, the reason why it's not a vector space is because... All right, so if you have 3s, 2 plus 5s. by showing that it is not closed under scalar multiplication. Find a specific vector u and h in a scalar such that. Okay, so what we're going to do, we're going to take, let's let s equal to 1. So then we get the vector 3 plus 3, 7. Okay, then we're going to scale that. So times 2. So then we get 6, 14. And then we try to solve the system. We try to solve s such that 3s is equal to 6 and 2 plus 5s equals 14. And we get s equals 2 for the first equation. And then we get, if we plug in that, then we get 12 here, which, so anyways, so what you do is you show that take s equal to 1, so then you get 3, 7. Then you take c equal to 2, so you multiply that by 2, so you get 6, 14. Then you try to figure out what s needs to be to satisfy that, and you find that you can't find an s. So therefore 3, this is actually a good problem. 2 plus 5s, not a subspace because not closed under scalar multiplication. Okay, that's actually a really good problem. All right, let W equal span of V1 to VP, where V1 to VP are in a vector space V. Show that VK is in W. Bro, this is obvious. Okay, you just take the coefficient for each VK equal to 1 for K and 0 for all others not equal to K. So this one I don't even need to write down. It's just so obvious, right? Show that VK is in W. First, write an equation that shows that V1 is in W, then adjust your notation for the general case. Okay, V1 is just good. So, okay, span is defined as a linear combination of V1 to VP. So you have, A V1 plus B V2, etc. So you take A equal to 1 and zeros for all other coefficients. And then you've shown that V1 is in W. All right, an n by n matrix A is said to be symmetric if the transpose is equal to itself. Let S be the set of all 3 by 3 symmetric matrices. Show that S is a subspace of the vector space of. Okay, this is cool. So this is cool. They didn't even. What's interesting is that they didn't even bring up that that 3 by 3 matrices form a vector space. So it's kind of interesting, but. What do we need to do? We need to show, 1, that 0 is in V. We need to show that for all u, v in A, u plus v is in A. And then finally, for C, so this is B, A. And then finally, for C, what do we need to show? We need to show that scalar multiplication is in, so C, so for all u, for all C, CU is in A. Okay. All right, so first off, 0. Okay, so let's just take 2 by 2s. The matrix of all, it said 3 by 3s. Okay, 3 by 3 of all zeros. This satisfies it being a 0 because any other matrix A plus this is going to just equal A. So that shows that 0 is in our thing. And obviously, the matrix of all zeros is symmetric because you take its transfer. I mean, it's all zeros, right? It's like not even worth saying. Then, to show that it's closed under, I'm just going to do a 2 by 2. Let's say we have A, B, B, D. So this is A. Then A transpose is equal to A, B, B, D. So the point is that then we take. Oh, wait. Okay, so that just shows that it's symmetric. But then we need, let's take C, or say E, F, F, G. Then if we add, this is B, then we take A plus B, we get A plus E, F plus B, F plus B, G plus D. So basically anything that's off diagonal is going to be added, so it's going to stay symmetric. So therefore it's closed. So U plus V is in A. Okay, and then finally we need to scale this. So we do C times A, we get C, A, C, B, C, B, C, D. So basically it's, no matter what, it's going to stay symmetric. So still symmetric. So therefore, symmetric matrices form a subspace. That's a pretty cool problem. All right. One sec. All right. Let V be the first quadrant. Yeah, see, this is what I was thinking. There's going to be a lot of these. But I remember that there were some that I was a little bit tripped up by. So let V be the first quadrant in the XY plane. If U and V are in, is, so this is true, right? It is actually closed under addition. The thing is that it's not closed under scalar multiplication, because if you just multiply 1, 1 by minus 1, then you flip over to the third quadrant. So that's that one. Let W be the union of the first and third quadrants. Okay, so here's the thing though. If U is in W and C is any scalar, I actually think that's true though. So what you need to do though is you need to take like, so yeah, so these are good examples, because this shows that, look, you can construct a set that is closed under addition but not a vector space. Then you can show that there's something that's closed under scalar multiplication but is still not a vector space because it's not closed under addition. So you take like 0, 1 and minus 1, 0, and then you get into the second quadrant, and that's not W. So W can't be a vector space. Okay, let H be the set of points inside and on the unit circle. Okay. Find a specific example, 2 vectors or a vector and a scalar. Wait, why don't you just take 1, 0 and C is equal to 2? Right? All right, I'll write these out. I'll write them out just for posterity. So 1A, yes. H, or yeah, V is V closed on plus B. You take minus 1 times 1, 1, not in V. Okay, 2, you say yes, closed on times, but B, take 1, 0, or 0, 1 plus minus 1, 0, not in V. Okay, there we go. 3, I think you can just take a vector and a scalar, you could just take 2 times 1, 0, not in H. Construct a geometric figure that illustrates why a line not through the origin is not closed under vector multiplication. Ooh, this is a good one. Okay, so yeah, so here's what you do. Let's do a little TL draw. I'm feeling energetic. Okay. It's probably gonna have a whole bunch of crap on it from before. Oh yeah. All right, let's do a new page or something. How do I do that? Okay, so you have XY axis, then you have this line. Okay, take this point to be U and this point to be V. Then U plus V is gonna be over here. It's not on the line. But when it's on the axis, then it's all collinear, so there's no way to get out of it. So this is actually really cool. So that's not in V. So there's the answer to that one. Determine if the given set is a subspace of Pn for an appropriate value of n. Okay, so 0 is clearly in it. Okay, so let's say P of t equal to AT squared is P of t subspace P of n. And I'm going to say yes. Wait, but first let's do it. So 0 in P of t, check. Then we take AT squared plus BT squared is equal to A plus B t squared. So it's closed. And then finally, scalar multiplication. C times AT squared. Just take CA is... Okay, so yes. It is. Okay, number 6. A plus T. So this is... So P of T is equal to A plus T squared. So 0 is in it. Wait, no, 0 is not in it. 0 is not in it. Right? Because if you take A equal to 0, okay, so basically what you want to show is that, what does 0 mean? 0 means it's an additive identity. But if we take A equal to 0, then P of T is equal to T squared. But let's say, then you take T squared plus AT squared, or A plus T squared, and you get A plus 2T squared, which is not in P of T, so therefore not a subspace. Cool, that was fun. All polynomials of degree at most 3 with integer coefficients. No, that's not. That's because if you had rational coefficients and it was and your scalar was the field of rationals, then I think it would be a subspace, but I don't think that this is, because you take all right, so this is going to be of the form, what is equal to A plus BT plus CT squared plus DT cubed. And then if you do that, but A, B, C, D are in Z. Just take your coefficient e times p of t, where e equals pi or something random, then you're not gonna, then it doesn't stay, okay, yeah, doesn't stay closed, so times not closed. That's what I'm gonna say, times not closed. Good. So 7 is done. Okay, number 8. All polynomials in P of n such that P of 0. Ooh, this is a good one. All poly in P of n where P of 0 is equal to 0. So, okay, so what does that mean? That means that the first, like, offset, like, let's say, like, in here, this just has to be 0. So we're going to get, like, a P of t is equal to, like, at plus bt squared, dot, 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 you know, an t to the n. And if you take a1 to an as the coefficients equal to 0, then okay. So 0 is in. So 0 is in P of t. Then we want to show that. Okay, so it's clearly closed under addition. So closed under plus, check, check, and then finally we need to show that it can be scaled, and it can be closed times. All right, so then I'm going to say yes. 8 is yes. I'm going to check my answers on all these because you don't want to mess this kind of one up. You want to get these right. And you want to get them right a lot more than you're getting, like, computation where you're just adding numbers together and stuff like that. Number 9. Number 9. Okay, so here we go. Let H be the set of all vectors of S, 3S, 2S. Find a vector in R3 such that H is equal to the span of V. Isn't that just going to be 1, 3, 2? Why does this show? So first off, all vectors of form S, 3S, 2S can be written as S times 1, 3, 2. So all linear combinations of that form. Anyway, so you can basically, I'll just say it's because it's a line through the origin, Okay. Why does it show it's a subspace? It's a subspace because you take S to be 0, then you have the 0. Then you take, let's say, S times 1, 3, 2 plus T times 1, 3, 2, and you get S plus T, 3S plus 3T, 2S plus 2T, and the linear combinations of that are still going to be, you just take S plus T times 1, 3, 2. So okay, so the linear combinations, it spans a line through the origin. Oh, and then closed under scalar multiplication, you just take S to be your coefficient, and it's fine. I think that's sufficient. Okay, let H be the set of all vectors. Show that it is. Okay, this is the same one. This is the same one. Okay, this is still just a line through the origin. Okay, now this is a plane through the origin because you have two free variables. So this is going to be written, so I'm not even going to write down 10, but for 11, 6b plus 7c, bc. Then we can write it as b times 610 plus c times 701. Find vectors u and v such that w is equal to the span of u and v. So then the vectors are going to be, yeah, okay, so we just did that. So you basically just strip out the b and the c into two separate column vectors, and then you're done. Why does this show it's a subspace? Because you've written it as a linear combination of column vectors, and that is like the definition of span. Let's see, what is the actual definition of span? Yeah, it's defined. It's the linear span of a set S of elements is the smallest linear subspace that contains S. Okay, but it is the set of all finite linear combinations of the elements of S. So yeah, so if you use that definition that it's just defined as linear combinations, then you're chilling. You're being chilling. Okay, this one, it's the same one as before. We can just move on. All right, I'll be right back. Oh, which one are we on? We're on 12. Oh, we're skipping 12. 12 is easy. Okay, 3, 1, 2. It's not in this. So no. How many vectors? 3. No. 3. B. How many vectors are in the span? Infinite. C. Is W in the subspace? Make it easy for me. Yeah, so you just add V1 and V2, yes? V1 plus V2. 8, 4, 7. I don't know. I'm not going to solve that. All right, let's just skip that. 15. What's up? Thank you, man. Still speed running homework. Dude, this week is going to be brutal, man. Let W be the set of all vectors of the form shown, where A, B, and C represent arbitrary real numbers. In each case, either find a set S of vectors that spans W, or give an example that shows that W is not a vector space. Okay, so this one's not a vector space because take A and B equal to 0. Wait, let me think. All right, so if we write it in parametric vector form, we're going to get 0, 4, 0 plus A times 3, 0, 1 plus B times 1, 0, minus 5. And okay, so so anyways, what I'm saying is you take A and B equal to 0, and then you get 0, 4, 0. If you add that to itself, you get 0, 8, 0. But that's not part of W. So then you just take 0, 4, 0 plus 0, 4, 0 is not in W. This is W. So it's not a vector space. All right, we'll do these for answers. Actually, wait, should we just or maybe we'll do it at the end. So not vec space. Okay, 6. Yeah, we'll just do it at the end. I'll use my answer and then we'll I'm guessing that this one's again not anything that's affine. I'm pretty much using that as what I'm saying. Like because you have this 0, you have this 1, 0, 0 vector that's in it if you take A and B equal to 0. This one looks like it is a vector space. So we're going to get A times 1, 0, minus 1, 0, plus B minus 1, 1, 0, 1, plus C 0, minus 1, 1, 0, and that's it. Okay, so this is, yes, it's a vector space because you take a, oh, well, I mean, the easiest thing to do actually in the previous examples is that you don't need to do this thing where take a, b, and equal to 0. You just show that 0 is not in this thing. You don't have a 0 vector. So similarly here, there's no, well, let me think about that. Because in this case, you might be able to make a 0 vector. If you take a equal to 1, no, I don't think you can. Okay, and then this one's clearly a vector space because you can do the same process as 7 is you just write it in as 3 different column vectors and then you're chilling. Okay, let's look at the answers for this one. Oops. Let's see how ChatGPT answers it. So my answers were not a vector space, not a vector space, and then yes and yes. Okay, not a vector space. A vector space must contain the 0 vector, but every vector in W has a second entry equal to 4, so there's no choice of A, B. Okay. Yeah, so here you try to find the 0, and you get a yeah. So if you just do this process, try to find the 0, and you can't, then you're done because it's not a vector space. Now here, this is a vector space because you do this process. That's what I was saying. That's what I did, and then so W is a subspace. W is a subspace. All right, so cool. So we get the same answers. All right, problem 19. If a mass M is placed at the, so wait, actually I wanted to ask though. I think you can, as long as, I think you can, because if you have a way to make 0, I don't know. If a constant term is independent. For example, yeah, wait. What really matters is whether your constant term can be reabsorbed by a reparameterization. The subset is if and only if it contains a 0 and is closed under some. So we said that there was no choice of A and B that, yes. Oh yeah, right. That's a good example actually. A plus 1, A plus 1. So if we had like A plus 1, A plus 1, then this would be equal to 1, 1 plus A, 1, 1. But since that, Right. So how to tell at a glance, can you solve the parameter equations to get the zero vector? If no, it's an affine translate and not a vector space. If yes, proceed, reparameterize. If solving for zero forces you to shift parameters, do it. If after that description becomes purely homogeneous, then you do have a set. Okay, so that was actually very insightful and a good clarifier. If a mass m is placed at the end of a string, and if the mass is pulled downward and released, the mass spring system will begin to oscillate. The displacement y of the mass from its resting position is given by what is taking so long? Dude, Desmos? It's crazy to me that Desmos hasn't been killed off yet. Like, there's gotta be something better than Desmos, bro. I think we have GeoGebra. Dude, what is with these things? Dude, I could make something better than this. Alright, I don't give a shit. I do care. I do care. I'm lying. Show that the set of all functions described with a W fixed and C1, C2 arbitrary is a vector space. Oh, that's cool. I like that. That's actually really cool. Okay, so show that y of t equal to C1 cos omega t plus C2 sine omega t forms a vec space. So wait. Omega is fixed. C1, C2 arb. Okay. So first off, we can get a 0. So we have a 0 where we just take C1. So we have 0 because we have C1, C2 equal to 0. It's closed on plus because then you just get C1 plus C3 cos plus C2 C4 plus C4 sine. And then scalar multiplication, let's say we have some d times C1 cos plus C2 sine becomes d C1 cos plus d C2 sine. So it's closed under that. This one's really fun. I like this problem a lot. What else do we need to show, though? We actually need to show a lot more. So associativity, that's sort of, we don't really need to show that. Commutativity, also don't really need to show that because you're basically distributing the coefficients. And since those coefficients are real numbers, then we can assume a lot of this stuff. So what else do we need to show? I think we showed it. We showed, additive inverse, add inv. We just take C1 or C3 equal to minus C1 and so on, and then we can get a 0. Then, let's see, we have additive identity by the 0 vector, so we have that. Let's see, let's duplicate this and let's go back to the definition of a vector space and just make sure that we're not missing anything. Because this is the kind of part of the book that I feel like you don't want to just skip over. Okay, so, all right, so we got the closure of it. We got the commutativity of it. We got the associativity of it. We got the 0, additive identity. We got the additive inverse. by inverting the coefficients. We got scalar molt. Oh wait, we got closure of scalar molt. We got scalar molt. Oh wait. Let's see if we have like C1 cos plus C2 sine plus C3 cos C3 sine or C4 sine. Then we get C1 plus C3, and we're trying to multiply that by a scalar. Yeah, so it all works out. It all works out. And then this, that also works out because you're just adding the coefficients, and then associativity of that's just given by the reals, and then multiplicative identity is obvious. Yep. Show that the set of all functions described in this is a vector space. So I think we're good. Let's see how ChatGPT answers it. But that's how I'm going to answer it. Oh, wow. Okay. So this is how it does the proof. Embed this family of oscillatory functions into the familiar vector space of all real valued functions with pointwise addition and scalar multiplication. Then all you have to do is show it's a subspace. So that's really cool. So what you do is you take it to be a subset of the real valued functions, which we assume from prior knowledge is a vec space. Then just show it's a subspace. So I'm guessing that this is like one of the more standard ways to do linear algebra proofs is that you just embed whatever you have into something that's even more general. And then once you know that it's a subset of an already well-known vector space, then you just have to show 0 and then closure under your operations, and then it's automatically a subspace. All right, 20. The set of all continuous real valued functions defined on an interval is denoted by CAB. This set is a subspace of the vector space of all real valued functions. What facts about continuous functions should be proved to demonstrate is indeed a subspace? So my guess is we need, so this is 20. We need closure under the operations. And we also need that f of x equal to 0 is continuous. Which, I mean, like, of course it is, but, you know. So the f... Oh, this is cool. I like 20, man. Wait, that's crazy. Whoa. Okay, so okay, wait. So just to like thoroughly answer A, the facts about continuous functions that need to be proved are that you can take two continuous functions and when you add them together, they're still continuous. Similarly, if you have a continuous function in some scalar, you can multiply that by any value and it should stay continuous. And then sort of as a degenerate case, you know, if that scalar is 0, you need to show that there's a 0 element and that 0 element is also continuous because otherwise you don't have closure. So basically just the definition of a subspace. Now B is a crazy one. So B is show that the set of functions f in CAB, so continuous functions on the interval AB, such that f of A is equal to f of B. So at the endpoints it's equal. Show that is a subspace. Okay, so the 0 vector is in, so let's call this set S. 0 is in S because take f of x equal to 0. Then f of A is going to, so then f of 0 is equal to, or f of A is equal to 0 is equal to f of B. So we have the 0 vector. Now we want to show, let's say we have f of, let's say we have f and g, then f plus g, we're at A is going to give us f of A plus f of g of A, which is going to be equal to, on the right hand side, f of B plus g of B. And since we know that f of B is equal to f of A and g of A is equal to g of B, then these cancel out and it's equal. And then finally, if we take C times F is going to be equal to, we're going to get CFA. We just want to show that it's still closed under our definition of our set. We need to show that it's in this set. So it's going to be so anyways, the point is, let's say you have this interval, and then you have these 2 points at the edge, and you scale them up and down, but you're scaling both of them by the same amount, so they have to stay the same. So it's closed under plus and times and has 0. Therefore, subspace. Cool. All right, 20 was fun, man. I like these ones about showing stuff as a subspace. I think that's like really fun. Okay, for fixed positive integers m and n, the set m by n okay, so they're telling us that m by n matrices is a vector space. That's the type of thing that you usually need to prove. Determine if this set H of all, okay, that's cool. So determine if H equal to A, B, D, 0 is a subspace of M 2 by 2. So I'm going to say, so we have a 0. We have closure under plus. And we have closure under scalar multiplication. Yes, it is. Yes, it is. 22. Let F be a fixed 3 by 2 matrix, and let H be the set of all matrices A. Let H be the set of all matrices A in M2 by 4, with the property that FA. Oh. Wait. Okay, 22 is I'm trying to think. Ooh, this is probably the best problem we've had so far. So F is 3 by 2. And then H is the set of A in M2 by 4, such that f times a is equal to 0, where 0 is in M3/4. So my initial reaction was that either A or F needs to be the 0, but that's actually not true. We showed that earlier in, I forget which section, but it's not the case that if you have matrices A and B, A times B equals 0 does not imply that A equals 0 or B equals 0. So, because like, let's say that you have the identity matrix 1, 0, 0, 1 is A, and then B is the off diagonal. Is equal to 0, but neither are the, yeah, so wait, I'll just write that out. Or actually, I don't have my Julia REPL open. Okay, so anyway, so 0 is in H. We know that because you just, okay, but now, or AF plus BG, H, CE plus DG, and CF plus DH. So I'm just doing it with square 2x2s. Hold on, I am gonna do a. Okay, so I just want to check. So we're doing this one. Let F be a 3x2. Let H be the set of all matrices in 2x4. That's a very good problem. Okay. So what I want to know is, like, let's say we have okay, let's say we have these three matrices. And then we have whoa. Can you not compare element-wise matrices? Oh, you can. Okay. Yeah, so the matrix distributes over addition. So that means that if you have, A times F is equal to 0, and you have A times G is equal to 0, then A times F plus G must equal 0. Well, we know it's a vector space. So we know that the no. Okay, so I think we're good there. So then therefore we have closure on plus. But I mean, one concern is I don't know if 2 by 2s is sufficient, really. But then also, okay, so now we need to scale it, and I don't know about scaling it. Is it the case that A times C times F is equal to C times A times F? Because if we know that, and I'm pretty sure we do know that. Oh, but it's epsilon away. Okay, so I think it is a subspace because we know that F times A equals 0. So then C times F of A is equal to 0. So then, but then C times F times A is equal to F times C times A. So implies that CA is in H. So it's closed on plus and times and has 0. H is a subspace of what? M 3 by 4 or M 2 by 4? Let's see how ChatGPT answers this. But I think that was the best problem so far, man. So it's using stuff that we haven't really. I mean, we know null space, but we haven't really proven theorems about this. Actually, when does just general linear transformations show up? I mean, I guess we already did it. Oh, here we go. Null spaces, column spaces, row spaces, and linear transformation. Okay. Look at this thing still loading. Hey, Desmos, you'll get there one day, buddy. What is going on? That's so weird. Okay. So we have the zero matrix, which is good. Closed under addition, yes. Okay, so you use the distributivity of matrix multiplication, and then you have scalar. Okay, so this is exactly what I did. Very cool. That was the best one yet, man. All right, true, false. 23. If f is a function in the vector space V of all real valued functions, and f of t is equal to 0 for some t, then f is the zero vector in V, false. 24. A vector is any element of a vector space, true. 25. An arrow in three-dimensional space can be considered a vector. Yep, that's true. 26. If u is a vector in a vector space, then -1u is equal to the same as the negative of u. True. 27. A subset H of a vector space V is a subspace if... No, that's false. That's a necessary but not sufficient condition. 28. A vector space is also a subspace. Yeah, by the definition of subspace it is. Yep. 29. A subspace is also a vector space. That is also true. 30. R2 is a subspace of R3. False. They showed that in the examples. The polynomials of degree 2 or less are a subspace of the polynomials of degree 3 or less. Yep, that's true. 32. A subset H of a vector space V is a subspace of V if it follows the 0, closed on plus, closed on... Okay, that's true. All right, so let's just copy those and make sure that we got them all right. Vector spaces are so sick, man. And you know what's so cool? Modules. It's getting rid of the part that requires the scalars are fields, and you just need a ring. You know what's even cooler, man? Freaking magma. Bam. I don't know why they don't just have a M type G cross G to G. Like, why don't they have this in there? Yeah, they go for more like traditional math looking things, and they don't use type theory, but I like the type theory definition. Anyways, all right, let's do this. 23 false, 24 true, 25 true, 26 true, 27 false, 28 true, 29 true, 30 false, 31 true, true. All right, nice, easy peasy, guys. These proof ones, I don't know if I want to do these ones. I was looking at these and it's like, Maybe we will. But I think there was a couple in here that I really wanted to let U and V be vectors in a vector space V, and let H be any subspace of V that contains both U and V. Explain why H also contains its span. Okay, so that's easy. Because H is a subspace, then it's closed under scalar multiplication and vector addition. So then that means that you have linear combination. Then you can you can take linear combinations of these, and it's still going to be an H. And the definition of linear combinations of U and V is equal to the span. So therefore, you can reach anywhere with the span with the linear combinations of U and V, which you know exist and are closed by the subspace of H. This shows that span is the smallest subspace that contains both. Okay. Let H and K be subspaces of a vector space V. The intersection of H and K, written H intersect K, is the set of V and V that belong to both. Show that H intersect K is a subspace of V. Give an example in R2 to show that the union of two subspaces is not in general a subspace. Okay, I like this one. Let me think. Okay, so I think I know how to answer this. Okay, so consider some vector that is in that's in the intersection. Then by definition, it's in H and it's in K. If V is in H, then, okay, wait, let's consider U and V that are in the intersection. So two vectors in the intersection. Okay, then they're both in both of the sets. So then we know that yeah. So then we know that that a linear combination of U and V stays in H because it's a subspace. So it contains the span of U and V. That same argument holds for K. But so now we've shown that linear combinations of U and V that were in the intersection are also in the intersection. Therefore, and for 0, let's see about 0. Well, 0 has to be in H and 0 has to be in K. Therefore, 0 is in the intersection. Therefore, it is a subspace. Okay, so that's easy. Now I want to know. Okay, I got it. This one's easy. So consider the line. So for 40, consider the line, the two vectors in R2, 1, 0, and 0, 1. Okay, so if you take the union of these subspaces, or I guess A times 0, A times 1, 0, and okay, I'll just write it out. It's much better when I have it. What's up? It's a subspace because it's just a line. No. That's with the picture, but you need to consider an arbitrary abstract vector space. And so you need to prove it like you would normally prove it. You can't just say, hey, well, look, it's a line. Obviously, you can for that, but think about function spaces and all that kind of thing. All right, anyways, so for union of, so consider A times 1, 0. Okay, so this is the linear combinations of it's basically the x-axis. Then we have B times 0, 1. Okay, so now we have the y-axis and the x-axis. If we take their union, we have a 0, we don't have closure. So this is not closed on plus, because if you take a equal to b equal to 1, then you get 1 0 plus 0 1 is not in the union of let's call this u and what do they normally name these? Oh, h and k. Okay. Huh. All right, given subspaces h and k of a vector space, the sum of h and k written h plus k is the set of all vectors in V that can be written as the sum of two vectors. Can be written as the sum of two vectors, one in h and the other in k. H plus k is defined as the set W such that W is equal to U plus V for a U in H and V in. Show that H plus k is a subspace. Okay, so you take U equal to 0 and V equal to 0, and since H and K are both subspaces, therefore they both have 0, so that's chill. So then we got the first condition. The second condition is that for some W, okay, so let's just write this out because this is a good problem. 41. H plus K is defined as the set W such that W is equal to U plus V for some U in H, V in K. Okay? Now we want to show it's a subspace. Okay, so 0 in H plus K because 0 in H and 0 in K. The interesting thing, though, to me that I hadn't really considered is how do you, like there are certain types of vector spaces that you okay, let's consider that H is this example where it's the subset of continuous functions on AB such that the endpoints are equal. Then we consider K to be yeah, okay, wait. I want to think about that. So let's say H is this the set of F on CAB where FA equals FB, but then K is equal to P, the polynomials of degree at most 3. Then what does W look like? Let's figure that out. I'm trying to I'll just talk it. I'm trying to understand sums of abstract vector spaces, and I understand that the definition, let's say H and K are both subspaces of some vector space, then H plus K is defined as the set of vectors W such that W is equal to U plus V for some U in H and some V in K. Now, to show that the sum is a subspace, you need to show that it's 0. And so you can just take the corresponding zeros from both subspaces. And then, but okay, here's what I want to know. Let's say that the two subspaces that we're trying to add together are really not as compatible as two subspaces of the same vector space. We could have a dimension 1 subspace of R4 and a dimension 2 subspace of R4, and it would be pretty natural to take their sum. But if we consider something more abstract, then how do you represent something? Here are two specific examples that I would want to know what their sum looks like. Consider H is the set of functions that are continuous on the interval a to b, such that the endpoints f of a and f of b are equal. Okay, so that's the subspace H, and it's a subspace of the set of continuous functions on the interval AB. Now consider the subspace K, that's a subspace of the set of polynomials, but K is at most degree, has polynomials of at most degree 3. How do you add those two subspaces together when they aren't subspaces of the same overall vector space? Bro, I love that I can just talk to it. Oh wait, but that one actually I picked a bad example because they are. Well, that's interesting, man. Oh wow, that's crazy. Okay. Yeah, that's crazy. I didn't even think about that. Okay, but does it have to be that the two subspaces are Oh, here we go. What if the okay, I didn't even read. What if you have two vector spaces V and W with no obvious common ambient, you can always form their external direct sum. That's what I was thinking. Okay, that's what I wanted to see. And you just do it component wise. That's so cool, man. Okay, so if we have W1 and W2, then W1 plus W2. Okay, then you just take U1 plus U2 and V1 plus V2. Now, if you scale it, CW is going to be equal to C times U plus V. But then you get CU plus CV. CU is in H and CV is in K. So it's a subspace. Show that H is a subspace. Oh, now that's interesting. You just take it to be 0. Yeah, that's cool. Okay, that one's easy. This one's fine. All right, so I think we did it. I think we did 4.1. We did it in style, and it didn't take too long. This is a good one.